Well, hello out there, everyone, and welcome to today's Cosmic Conversations. My name is Mary Holt, and I work in the planetarium at the California Academy of Sciences. And I'm so excited to be joined by Sophia Gad-Nasr, who is a PhD candidate in cosmology at UC Irvine. Hello, Sophia. How are you doing this morning?
Great. Really happy to be here.
Awesome. So glad you're here. And we're going to be talking about some of the most dark and mysterious things in the universe today, black holes, dark matter. And if any of you have questions about those things, as I'm sure you will, feel free to drop those questions in the comment box throughout the show. We'll do our best to address them as we go along. But do you want to give us any sort of intro to how you got into this work, Sophia, or like what it is that you do with your research?
Yeah. The reason why I got into astronomy in the first place, into, I guess, loving the universe, I wasn't the typical child that always knew that I wanted to do this. I was kind of like, I thought that I was supposed to be like a medical doctor because that's kind of like what my dad wanted me to be, and it didn't work out for me. So I wanted to figure out what I wanted to do. And when I went into undergrad undecided, I joined an astronomy club, started to go to star parties, started to, go to the talks and everything. And that was it. I was just like, okay, this is what I want to do. So it was really an astronomy club that opened this up to me. And then a professor at my undergrad institution who was working on dark matter in the way that I work on it now, basically ushered the way to my career.
Nice. That's so cool. It's interesting. That's like, I feel similar to my journey to get into planetariums. It's like astronomy club in college, and then
Yeah.
they hook you.
Yeah, they're really important.
Yeah. And I know we're going to start out with just talking generally about what is dark matter, right? So you want to kind of intro us into that?
Yeah. So I'm really excited to start talking to talk about all this stuff to you. We're going into the dark side, and so turns out the universe is overwhelmingly dark. 95% of it is stuff that is dark that we don't understand. What do we mean by dark? Really, that we don't understand it and that we can't see it. 70% of this stuff, or 68 in particular, I usually just round it off to 70%, is dark energy, and this is stuff that we understand far less than anything. It is causing the universe to stretch apart faster and faster with the progression of time. And that's pretty much like all we know about it. We're still trying to figure out what that is. Then we have 27% of the universe is owed to this stuff called dark matter, which is really similar to the kind of stuff that we're made of, except it doesn't interact in the same way. And so we can't see it and we can't feel it. And it's 5 times more abundant than the stuff that we're used to, which is just you, me, the sun, your dog, everything that you can touch and see and feel. These are things that we're used to. And we're actually only like 5% of the universe. So we're a really small minority of that. And so today we're going to focus on dark matter because this stuff is really cool. And I wanted to make a distinction between the two because a lot of times people might confuse dark matter and dark energy. They're very different in that dark matter is actual stuff, like it's matter, it's mass in the same way that we are. It just has different interactions. Whereas dark energy is something that's just causing the universe to stretch apart faster and faster with time. It's not stuff in that way. And we understand it a lot less than we do dark matter.
Mm-hmm. I will say, I feel like the names for each of those is actually remarkably good when it comes to astronomy things. Often the name does not match at all what the object or thing you're talking about is. So it's actually pretty impressive that these are fairly good descriptors.
They are, yeah, they are pretty good. Yes, astronomy is creative. I would say astronomers are creative in naming things, and sometimes they get it well, and sometimes they don't. Okay. And so one of the things that is kind of like a smoking gun, if you will, for dark matter, for the existence of dark matter, is the bullet cluster, which you're seeing right now. So what the bullet cluster is 2 clusters of galaxies. A cluster of galaxies is just basically a bunch of galaxies that are gravitationally bound to each other. So they're always kind of like a unit. And so this is something important as well. So dark energy, when it stretches the universe apart and moves galaxies away from each other, stuff that's gravitationally bound will not expand or expand away from itself. So a cluster will remain a cluster, but it will move away from other clusters. So that's one thing to note. And in this image, what we're seeing is two clusters of galaxies. And if you look at like the bluish color, those are where the two are. These are two clusters of galaxies that have passed through each other. And so galaxy clusters are actually overwhelmingly full of gas. And so there's about 10 times more gas than there is regular matter, than there is stars, rather, because gas is also regular matter. But there's 10 times more gas than there is stars in mass. And so stars tend to just pass through each other. They don't interact because there's so much space in between them, whereas gas will experience drag. And so what you're seeing in this image is when you look at the sort of the blue parts are let me start with the pink. Actually, I want to start with that because the pink part is where the gas is. And so one way that we wanted to test whether it's true that there's dark matter or whether it's just regular matter, and that's just what it is with this cluster, because we have a situation where stars will just pass through and not interact, but gas will not. And there's 10 times more gas in a galaxy cluster than there is stars. So naturally then, as we can see where the pink is, that's the gas dragging behind the two galaxy clusters, which are kind of where the blue is, okay? Mm-hmm. So if we do a sort of gravitational potential, if we try to map how much stuff there is where, we should then, if there's no dark matter, we should see that the pink area is where most of the mass is. But that's not the case. Still, most of the mass resides in those blue areas, which are actually, the blue is done from gravitational lensing, which we're going to talk about in a few. And
yeah, I was going to ask, actually, are these colors, representing temperature? Is this any sort of like real color, like accurate color, whatever, what you would see? What is the color representing for each of those?
Yeah, no, it's just sort of to distinguish between the two. The gas is actually, it's actually gas, but the blue comes from just gravitational lensing.
Oh, okay.
So it's just gravitational lensing tells us how much mass there is in something, and we're going to actually talk about that shortly. So, but what we find is that, you know what? Let me give a little bit of an explainer though. So Einstein's theory of general relativity basically said that mass bends space-time. And so with a galaxy cluster, you have a huge mass in space-time. It should bend it a lot. And so if mass didn't bend space-time, then if we had a galaxy behind this galaxy cluster, you wouldn't see anything at all. It would be completely blocked in the same way as if you were to put like a bottle behind a bush. You can't see it, right? Mm-hmm. Well, in this case, if it does bend space-time, then you would see sort of warped galaxies around this cluster, and that's actually what happens. And you've probably seen a lot of these images before. We're going to show one in a few slides. We'll get to that, where you can see these sort of arcs around a bunch of galaxies. Those arcs are actually galaxies that are much further behind. And because that galaxy cluster is bending the mass in front of it, bending space-time in front of it, and light does travel on straight paths along space-time, but space-time is curved due to the bending of them, or due to the mass bending it, and this is why we get these arcs around it. And so that's what gravitational lensing is, and through that we can actually infer how much matter there is in a galaxy cluster. And so with that, that's how we know that, for example, the bullet cluster is like what, some people call it a smoking gun for dark matter, because the overwhelming amount of mass should be where the gas is if there is no dark matter, but yet it still resides where the stars do. And so we could talk a little bit more about how we know it exists. Mm-hmm. And the most
kind of the very obvious example, right?
Exactly. Yes. This is the one that most people have heard of, rotation curves. Mm-hmm. So we have a pretty decent and large sort of cosmic, solar system scale size laboratory, if you will, to test gravity. And when we do that, we can do that by measuring each planet and how it's affected by the overwhelming mass in our solar system, which is the sun. And so when we do that, we find that the force of gravity is decreasing the further away that a planet is, and the force of gravity it also determines how fast a planet moves. And so the further away a planet is, the slower it will be moving around the sun. So we expect the same in a disk galaxy, which is like our own, or Andromeda, for example. And so because they're all kind of, stars are also orbiting along a plane around a center. So what we expect to see is this dashed curve over here. That's what the solar system looks like. And that is basically our expectation from gravity as we understand it. But what we actually see is something more like this. So it doesn't make, the further out you go. Exactly. And so the further out you go, you don't move slower. It sometimes, in this case, they move a little bit faster, and often they just move at the same speeds. So it's like, it doesn't make sense. There's just not enough matter, or there's not enough stars, or even gas. If you were throwing gas there's not enough of that to be able to explain this. So there has to be something else in there, like giving these stars an extra gravitational push and giving them these extra speeds. And also without that, if they were just moving this fast, galaxies would have flown apart. So we'd need something there to be giving it that extra gravitational push, as well as holding these galaxies together. So that's one thing that tells us that dark matter exists. But and I want to pay some respect to Vera Rubin, who is she and Kent Ford in, I think, 1969 or 1969, and then they published their paper in 1972. I might be wrong, but let's say 1970s. She and Kent Ford went and did all these measurements on the Andromeda galaxy and found like the first like sort of, I guess, ironclad evidence that dark matter exists. It was inferred in the 1930s by Fritz Zwicky, but it was inferred incorrectly. And Vera Rubin is the one who's actually, I would say, like, kind of discovered that this is an actual thing. We have galaxies that move in ways that don't make sense. So I wanted to just pay some respects to her.
And to point out, too, just how wild it is that they discovered that in that time. It was only in the 30s or so that we began to realize that there were, in fact, separate galaxies. So, like, only, 40 years later, we're like, oh, and there's dark matter.
Right, exactly. Cool. Yeah. And that's actually something that blows my mind a lot, is that, like, less than 100 years ago, our universe was the galaxy.
Yeah.
So we've made some pretty huge strides. But I wanted to move on to some other evidence, because oftentimes people hear about rotation curves and that's about it, which can be explained in other ways as well. But there are things that you can't explain without dark matter. And here's one of them, gravitational lensing. So now we get to talk about the gravitational lenses that I was mentioning earlier, and how we got the bullet cluster, the blue sections in the bullet cluster from gravitational lensing data. So you could see all these, like, sort of arced features over here. Those are galaxies that are behind this galaxy cluster. There are multiple. It could create multiple images as well. There's a video that's up on your end if you can.
Yeah, looks like Ryan's scrolling us through it right now.
Perfect. Yeah. So you can. So do you see how they multiply and just kind of like move around? That's what happens if you put a galaxy behind a galaxy cluster and move it across. It kind of shows you. I really like this because it shows you sort of how images become multiplied and how they become warped. So
this video is based on data from multiple images that we've actually taken, right? It's kind of a spliced together. Is that correct for the video, or how?
So that's actually like a simulation of it. That's actually the Whirlpool galaxy that you're seeing moving behind it. So it's just taking, like, if I was to take a galaxy and put it behind it, that's what would happen, kind of thing.
Got
So it's a simulated version of a galaxy cluster.
Okay.
Or a gravitational lensing, rather. Okay, and I mean, if you do observational astronomy, then you would have recognized that as the Whirlpool galaxy as well. So gravitational lensing, through this, we can infer how much mass there is in the galaxy cluster. And even, you know, when we count up all the mass due to the stars, including the gas, which is, remember, 10 times more, there's 10 times more gas than there in mass than there is stars in galaxy clusters, it still can't explain these lenses. There has to be dark matter. And another way is large scale structure. So this goes to,
so I think we're going to switch to my planetarium software I have ready here.
Yes.
Cool.
So large scale structure.
There we go.
If you zoom out,
so we're looking at the Milky Way galaxy here, which we were rotating around when we started. I'll zoom out slowly.
Great. Yes, and as you zoom out, we're going to start noticing these webs and sort of filament features and stuff like that. That the way that these are formed, it has to be something that wasn't interacting with light. So in the early universe, this kind of ties into the explanation for with the cosmic microwave background as well. In the early universe, when everything was super hot and dense, matter and photons bounced off of each other all the time, and so you didn't get atoms created. You didn't get like molecules and atoms and stuff like nothing could hold together because it would just keep getting hit out by photons. And so we had these little dense pockets, and you can kind of see like the sort of dense features, the denser regions around here. Those are like the denser pockets. Exactly. And so because matter in general, dark matter or regular matter, interacts with gravity, it'll want to fall into those denser regions. When normal matter did that, it got kicked out by photon radiation, just like that, because photons would interact with it and push it out. So yeah, so you could see in there like a lot of the really denser features. But dark matter,
and just to be clear for everyone too, so all the individual dots we're seeing in this are all individual galaxies that we're looking at. Yes.
And this is at really large scales. We've zoomed out so much. And so I'm just trying to find my spot.
You're saying how early on.
Right. Yeah. So matter, regular matter or normal matter couldn't fall into these dense pockets and just stay there because photons would kick them out. But dark matter was able to. So it went in there, created these pockets that ended up looking like these really cool filaments that later on, once the universe cooled off enough and photons roamed free and stopped, kicking normal matter around and kicking electrons out and stuff like that, then the normal matter was able to fall into where the dark matter was, creating this giant cosmic web. That's something you can't do without dark matter. You can't create this. And finally, we're going to go to the cosmic microwave background.
So I'm going to keep zooming out. So we're now looking, we're essentially looking back in time several billion years to a few 100,000 years after when we think the Big Bang would have occurred. So that's where we're at right now.
Yes. And so that's about 400,000 years after the Big Bang?
I think so, yeah.
Yep. And so on the slideshow, if we can just show the slideshow, because often I think people have seen this image, and this is what the cosmic microwave background is and what you're seeing in the planetary or in the software.
Orange here is the same as this map here.
Yes. And so this is basically, it's like a whisper of the Big Bang, we call it. It's as far back as we can see, because beyond that is still when photons and normal matter like interacted and stuff like that. So it's kind of like opaque in a similar way as you can't like look through the sun. You can't look through the cosmic microwave background for that reason, because in the sun you have photons bouncing around each other as well. So I like to use that as an analogy, is opaque. And so, but in this, we have so much information. When we take, and what this kind of tells us is like the different colors that you see are density fluctuations and temperature differences. And so the differences in temperature and density fluctuations, when we plot these out, if you had the information that we get out of it, we see there's a plot that's called that comes from like a I don't want to get too into detail with that. But what we can find from here is how much matter there is, how much regular matter there is, and how much dark matter there is, as well as how much dark energy there is. If we didn't have dark matter, the information that we would get out of it would look different. And so you can't. This is something that also can't be explained without dark matter.
So essentially, things wouldn't have kind of clumped in the same way if you didn't have dark matter. Right.
Exactly. Okay. And you wouldn't end up with, like, there's just not enough time from then until today for because if we just had regular matter, you could get galaxies and stuff like that, but you would not get the structure that we have today. There's not enough time to do that, because regular matter would be sort of kicked out and all that stuff. So it would take a lot of time for it just to be able to fall into these dense regions and form galaxies and stars and whatnot. And you wouldn't get the structure that you see today. So these are things that require dark matter, literally require dark matter to explain.
So it looks like we have a question from a viewer wondering, is dark matter just the big unknown?
It is
totally
an unknown.
Or I think you're about to tell us a little bit more about what we think it might be, right?
Yes, it's definitely an unknown in that we have not discovered the particle yet.
Sure.
But we've increasingly learned sort of what it isn't, and we've tried to use different models that would work to be able to create the structure that we see today. And one of them that I use is called self-interacting dark matter. And if we can get the illustrious video up. Yeah. So in this video, what you're seeing is illustrious is a simulation. Now you're starting to see gas as well. So illustrious is a simulation of the universe that uses sort of a standard paradigm of dark matter that doesn't interact with other dark matter particles at all. And that's really successful at explaining the universe at large scales. But when you zoom in, we find problems at the dwarf scales. And so self-interacting dark matter, it was proposed to resolve that. And that's the type of dark matter that I work with. And it brings out like this, it's really cool because it brings out the possibility of having dark forces that we don't understand as well. So it would be kind of like sort of like a whole dark sector where, maybe it's not just one dark matter particle. There might be some dark matter particles as well as some dark forces as well. And so
sounds very spooky.
And with this, it's able to explain the dwarf scale galaxies as well as large scales very well. The cool thing about it is that the way that the mechanism behind self-interacting dark matter, so dark matter sits in galaxies kind of like in halos. So it kind of surrounds galaxies in this giant halo. The way that it behaves eventually in time could cause the dark matter to actually collapse in on itself to a point that where it can collapse into a black hole. And the reason why this matters is because at the center of every large galaxy, we see supermassive black holes, and we don't understand how those formed. So let's talk about a little bit about what black holes are in the first place. So if you take a region in space and stuff a whole bunch of matter into it, and you put way too much in, then it just collapses in on itself, maybe kind of like tears a hole into space-time, and you get this black hole from which not even light can escape. if you get close enough. So it's a huge, it has huge gravity, and so not even light can escape. So so this is how, and the way that these things are created, at least stellar mass sized black holes. So these are like black holes that are up to like say 50, let's say even 100 times the mass of the sun. These are ones that are formed from really massive stars that die. So when massive stars explode in supernovae, what happens is if they're really massive, there's pressure that pushes out supernova and pushes out stuff. But then if there's too much stuff, then gravity kind of takes over and says, no, you got to come back here. And it pulls it all back in. And then there's this sort of never-ending collapse into a black hole. And so we understand how stellar mass black holes are formed. That's cool. The problem is, when you look again in the centers of large galaxies, there, we have the center of our galaxy has a supermassive black hole that's 4 million times the mass of the sun.
I have that model we can show of the center of our galaxy, actually. So here's the Milky Way. And like you were saying, there is a supermassive black hole in the center of the galaxy. So I'm diving into the center of our galaxy here.
Yes.
And we've got this cool, this doesn't tell us how this black hole formed, the supermassive black hole, but it shows kind of how we know it's there, right?
Yes, exactly. And by plotting, so all those little tracks that you see are actual stars plotted that are moving around this galaxy, this supermassive black hole.
Yeah, because if you look at the center of where all these are orbiting, if I zoom in real close, you're not going to see anything, but we see them moving around something.
Exactly, which makes sense, right? Because we can't see black holes. When you do so, I guess at some point we'll get to see the image. The black hole that was imaged in M87, that's a 6 billion solar mass black hole. So it's 6 billion times the mass of the sun. The reason why we could see anything is because it's accreting matter, so it's eating stuff. Okay, and it has matter swooshing around it. Our black hole doesn't do that. Our galaxy supermassive black hole doesn't eat right now, and so you can see in radio waves. The problem with that is the problem with imaging ours. Like, so the reason why they imaged one that is like, I think 5 or 50 million light years away.
Yeah, and I'm zooming it back out so we can see the direction that one is. So we've got ours is in the center, the Milky Way here. But then the one that we got an image of, M87, is over there. Very, very far away. We don't have a super nice model like the Milky Way, but I do have a little image here of it that we can see.
Okay, great. And we can put up our lovely black hole image right here.
Yeah.
So, so yeah, and the reason why they imaged that one and not the one at the center of the Milky Way, like this is all in radio waves, so it's not visible light. It's radio waves, radio wavelengths, because we're in this galaxy, and so we have to look through a lot of dust. So it's really obscuring. It's really obscuring our view. Whereas looking out there, we had a clearer view, and so that's why they chose to image this one instead. And so we it's not so okay. You one person, or rather, people might think, okay, but hang on, like our universe is 13.8 billion years old. Maybe there was enough time for black holes to have, merged and accreted matter up until they reached, I don't know, maybe 1 million or 1 billion times the mass of the sun. The problem is we find these only 700 million years after the Big Bang. That's not enough time. That is not enough time to form these things, and so there are some possibilities for that. One way that we try that people have tried to explain it, or rather, like physicists and astronomers have tried to explain it, is perhaps in the early universe before metals were formed. Okay, yeah, let me explain something. In astronomy, there is hydrogen and helium, and anything more massive than that is called a metal. It's just how it is. So a metal is anything more massive than hydrogen and helium. So way back in the early universe, before stars were able to fuse and create metals, where we just had hydrogen and helium, perhaps there were supermassive stars that are like 1,000 times the mass of the sun formed, and in which case they would, kind of they would give us maybe not 1,000 solar mass black holes, but something, maybe like 500 times the mass of the sun.
Which, just to make sure, we don't see 1,000 solar mass stars currently, right? We haven't observed anything that large yet. Okay.
The largest mass one I think we've seen is about 200 and something times the mass of the sun. It's still pretty big, still pretty massive. But yeah, no, we don't see that. Mm-hmm. And we actually still haven't seen stars that don't contain any metals. We haven't seen stars that are just purely hydrogen and helium just yet. Those are called population 3 stars, which we're hoping that the JWST, the James Webb Space Telescope, will give us more insight on. So that's one possibility, but at the same time, again, that doesn't really, it's not enough to explain how you would get 1 billion times the mass, a black hole that's 1 billion times the mass of the sun, only 700 million years after the Big Bang. So there's another cool mechanism, which I like this one. It's called a direct collapse black hole. And so it's like when gases come together to form stars, you have these just giant clouds of gas that kind of come together. And today, because we have all the elements that we do, like we have metals, so things that are heavier than hydrogen and helium, these things cause these gas clouds to kind of break apart because it just the way that the intermolecular things and it's sort of like these kind of interactions that cause cooling, which really just causes these clouds to break apart, and then they form stars first. And if they're really massive, then those stars die in supernovae that end up in black holes. But if, again, in the early universe, when we didn't have any metals, then you have these giant gas clouds that come together and they don't break apart. So all that happens is that there's just so much stuff in this one spot, and instead of going to the star phase, it skips that entirely and just collapses into a black hole, which is really cool. It requires a lot of conditions, and so it's a very cool idea that can actually give us really massive seeds for black holes that are like 100,000, even a million, up to a million times the mass of the sun. So these are really good. Those are good seeds. Those are good seeds to be able to explain something like that. However, the conditions that you require, there are a lot of conditions that you need in order for that to be able to happen, and they all have to be met. So now self-interacting dark matter it gives us a mechanism where eventually what happens, because self-interacting dark matter, it just tells us that dark matter particles do interact with each other, where the standard paradigm says that they don't at all. They just kind of don't see each other. They'll just pass through in the same way that dark matter passes through us. They also pass through each other. Well, self-interacting dark matter says no, there's a dark force that mediates these interactions, and dark matter particles do scatter off each other. And that process eventually leads to dark matter halos condensing into the center and collapsing into perhaps a black hole. So there's a natural way to be able to explain how really massive seeds like that could be formed that early in the universe. And this is something that my work is exploring right now.
That's so cool. Dark matter, black holes.
The beautiful thing is it's kind of like a twofold thing, right? There's two questions. One is, what is dark matter? We don't know the answer to that. Another one is, how are supermassive black holes formed? We still don't know the answer to that. So it gives us kind of
connected.
Exactly. It's like a sort of I don't like the two birds with one stone thing, because I like birds. But you kind of get 2 for 1, let's say. Yeah. So I like it, of course. And that's what my work explores.
Nice. That's awesome.
Yeah.
Cool. And I think, I think we showed all the things we were going to. I don't know if there are any questions in the chat.
Yes, let's see.
I know we answered one of them. Was there anything else you wanted to make sure to cover before we wrap up, or?
No, I think the biggest thing that I wanted to just mention is that I think that my prediction is that the next big thing, and I'm happy to be wrong. That's cool. But my prediction would be that the next big thing that we learn about, really big thing, is going to be dark matter, and it's going to be a particle. So a lot of ways that people try to explain dark matter, or one of the ways that people try to explain dark matter away, if you will, is by modifying gravity. And so the evidence that I had showed you earlier, the rotation curve, so like the way that stars move around galaxies can be explained that way, but nothing else can. And so it is possible that we don't understand gravity entirely. Like, you know, we went from Newtonian gravity to Einsteinian gravity. And so it's possible that that's true. But regardless, even if that's true, dark matter still is necessary. So even with modified gravity, like all the types of modified gravity that actually can explain anything, that the other things that I'm talking about require the addition of dark matter. So essentially what you're doing is further complicating already complicated equations, which is not really a pretty thing to do in physics, to end up doing exactly the same thing that we do in the first place, adding extra matter to the picture. And so it's just, you know, it's not in its current form. That's not going to be it doesn't work. It just doesn't work. Just to put it bluntly.
Awesome. Well, thank you so much for this talk. This was super interesting. And I'm so glad you got to join us. I know that our producer Ryan did share your Twitter link in the chat, so if people want to follow you, and you can also see her I can't really point at it, but right below Sophia is the handle as well that you use on Twitter and TikTok. I'm one of your TikTok followers. You're great. So be sure to check her out on those platforms. But with that, I want to thank you again, Sophia, so much for joining us, and maybe we can have you on for a future thing in the future. That would be great. But I hope that everyone enjoys the rest of their day. And if you're interested in more live streaming programs, we have a lot on the Morrison Planetarium Facebook page if you want to just check that out. And next week is our final Cosmic Conversations, actually. So be sure to join us next week as well for that. But with that, I will say stay safe, stay healthy, everyone, and have a great day.